Look, it's a limit as a process.
Nope, Chuck Testa.
Oh my gosh, is that a limit ordering a soda? Nope, Chuck Testa.
Wait, is this Hokey Bird getting infinitesimally close to the limit?
Nope, Chuck Testa.
So, we've been talking about what limits are, but we figured it was time to talk about what a limit is. To do that, we have this nice function here, f of x. And by nice, we mean this function is continuous and smooth and differentiable, and all of those nice things that we really care about. Now, there's some input a in this graph. And because we can see this graph, and we know that this function is nice, we can see that it should give us that f of a is equal to L. Now, if we wanted to evaluate the limit of this function at this point a, as x approaches a, we can see that it should equal L. But we don't know that for sure. So we need to find a way to prove that the limit of this function as x goes to a is going to be equal to L. And to do this, we should probably look at the definition.
The limit as x goes to a is equal to L, and we'll write this as the limit as x goes to a of f of x is equal to L if given any epsilon greater than 0, so we have an epsilon greater than 0, there exists a corresponding delta that will give us a delta greater than 0, such that the absolute value of f of x minus L is less than epsilon whenever the absolute value of x minus a is less than delta.
So, Miss Brown, we have this formal definition of a limit, but what the heck does any of this mean?
Well, the best way to talk about that is to take it step by step. First, we see that the limit as x approaches a, so we have an a value right here, will give us a value of L when we evaluate that limit. So, the definition first says that we have to find some epsilon positive and then the corresponding delta that is also positive.
Epsilon and delta? I don't get that.
Well, we're taking an epsilon neighborhood around an L, and then we have to figure out what delta neighborhood around A will place us within this neighborhood.
Neighborhoods? The only neighborhoods that I know about are where I grew up.
Well, we have an epsilon positive, so we can add that epsilon and get this upper bound, and we can subtract that epsilon from L and get this lower bound. And we do the same thing with delta down here. We have a delta positive, and we can subtract delta to get this lower bound, and add delta to get this upper bound.
Oh, I think I get that. So basically, someone else is going to give us some epsilon, no matter how small it is, and then our job is to find a delta that matches that epsilon. Does that make sense?
Exactly, you've got it.
Okay, Miss Brown, I think I understand the definition, but how do we apply this?
Okay, let's look at this example. We have the function y equals x squared, and we'll say that our a value is equal to 2, which would mean that our L value we would expect to be 4.
Okay, so what's the first step? How do we start to figure this out?
Well, why don't you pick our epsilon?
Okay. I'm going to pick a really small number. Let's go with 0.1.
Okay, so then what would our upper bound be?
Oh, okay, so it would be 4.1.
Okay.
And then our lower bound would be 3.9, right?
Good.
Because it's L plus epsilon and L minus epsilon.
Exactly.
Okay.
So now we need to figure out which delta neighborhood will put us to that corresponding neighborhood.
Okay. And then that's your job, once I pick the epsilon, to pick the delta that matches that epsilon?
That's smaller than that epsilon.
Okay, smaller. Okay, that makes sense.
We'll do a neighborhood of 0.02. So this lower bound would be 1.98, and this upper bound would be 2.02. And this works. So that means that any value that we pick in this range will always map in to this other range that we've selected.
Okay, I think that makes sense. Because if I were to do 1.98 squared, plugging that into the function, that gives me a value of 3.9204, which maps into this epsilon neighborhood that we talked about earlier. Is that right?
Exactly.
And then, well, let me try in the other one. If I do 2.02 squared, that gives me a value of 4.08, which also is in the range. Okay, I think I'm starting to see what this means.
Is this epsilon too small?
Nope. We can find a delta in there.
Is this epsilon too small?
Nope. We can find a delta in there.
Is this epsilon too small?
Nope. We can find a delta in there.